So what we've got here, this is actually a this is a 3D equivalent of that noise contour plot that people can zoom in and out of, and they can spin around and they can get a contextual idea. So you get a mouse highlight of the L-den value, which is just a sort of decibel level of the noise that's induced. So you can see here we've got a busy road coming through the center of town. But really what I wanted to do, this is useful to look at, this slide. Oops, sorry about that. Because it gives an idea of the amount of data that we need in the background in order to sort of generate those numbers. So what we need is an idea of the fully explicit buildings data. We need to know surface definitions such as tarmac or vegetation or water, because they all have very, very different noise attenuation characteristics. You can imagine noise propagates much more quickly over open water than it would do through a forest. And so we need to build all of this and integrate all of those data into our model. And our aim really, principally, is to automate the whole process. So the consumer comes along and just provides us with a postcode and a house number. And within timely fashion, we sort of therefore spit them back a report of environmental noise on properties they're interested in a clear and understandable form for the person in the street. You know, you shouldn't have to be an acoustics expert or a sound engineer in order to understand the data we're going to provide. So who are we? Well, we're a small startup based in North Somerset. And my colleague, Laurie Vaughan, who's actually on the call here, he was the founding director and he was the one who came up with this idea. And as with all good ideas, it started over a beer and a curry. And now we're a small startup. So, and, you know, getting to a stage where we can offer this as a commercial service. I do have a slight disclosure, well, a full disclosure to make really. We're both mechanical engineers by training. Neither of us is a geographer or a GIS specialist or a computer scientist, but we do have a long background in sort of using numbers, interesting numbers, to do interesting things. So fundamentally, the question becomes, what is noise? It's not a sound. A sound is the phenomenon of pressure waves traveling to and from through a medium, most likely in air, or unless you're singing in the bath or you've got the cup against the neighbor's wall. And in our context, noise is an unwanted or unpleasant, loud or disruptive sound. And that's according to the Wikipedia definition, which, as we all know, is always right. And it's worth noting, sound is quantifiable. You know, thanks to Bell Laboratories, we've got the decibel scale, but it's not an easily understandable scale for the consumer in the street. You know, does anybody here know if 10 decibels is a loud noise or not? Possibly not. Whereas noise, on the other hand, is a subjective measure. You know, everyone who's had the misfortune or fortune to watch an AMSR video in lockdown will attest to that. But more importantly than anything, high levels of noise can be quite harmful to our health and well-being. And that's been studied objectively, and there's a genuine concern. And really, so much so that policymakers are starting to pay attention to this. But perhaps a slightly facetious example here, but, you know, Jimmy McNee has a particular sensitivity to noise, but I'm not going to make any judgment on that. So how do we do it? Well, I had to slip in an Amazon Web Services diagram, horrifying to any sysadmin, I guess, amongst you, but I think it looks nice. And it gives an idea of the sources of data that we're using, aggregating. So geographical data inform the Ordnance Survey and OpenStreetMap data to give us an idea of the traffic and rail networks, and also to give us an idea of the distribution of vegetation and road surface and open water geometries. And then we also suck in traffic data from the Department of Transport's repository, and we can bring in rail and air, so ADS-B air traffic data as well, and integrate this all into our single model. And then what we use is just some open source noise modeling software to then predict the levels of distribution, the levels and distribution of noise at these various sources, or from these sources at a location of interest. So this evening, what I want to do is really just to run you through how we go from Department of Transport traffic data to a noise contour map with no particular user interaction bar the input of a postcode or a house number. I mean, there are a lot of other data in the background we need to process, but I'm just going to focus on road traffic data this evening for the example. And I must confess, we're standing on the shoulders of others really, and what we're doing is tying together the functionality of lots of different libraries, just with a bit of Quiet Place's special sauce to bring it all together. And so it's mainly what I wanted to give you is a sort of glimpse behind the curtain really, but hopefully of some interest, because it touches on how we process geographical data, and also how it can be done in a relatively straightforward manner using pretty commonly available tool sets. So the example I'd like to show is that this is the road network around Derby. So it's a sort of mid-sized city in the Midlands of the UK for those outside the UK. And I was careful to say network there, because that's really the primary focus of what we use, the data we use. So this network here is easily downloaded from OpenStreetMap, for example, or from the Ordnance Survey, amongst others. And for our purposes, specifically, I found that the OpenStreetMap is the most easily used. Whilst the Ordnance Survey data is really fantastic and accurate, at this network level, it makes some slightly different simplifying assumptions at road splits, for example, that cause a bit of a headache in terms of modeling. So what we do, we read this into a Python network object, or network X object, and that gives us a multi-digraph representation of this road traffic network, meaning that we can account for direction of travel, we can account for one-way roads, and so we can build up a reasonably high level of detail in terms of our traffic model. But we also convert that into what's called a dual graph. So that's kind of an inverse of what you might expect, with nodes being intersections and the links between them being the road segments. A dual graph is the reverse of that. So you then consider a road as the nodal point and all the intersections between them as edges. And what that allows us to do is to account for sort of angular change as you progress through the network, which is a subtle difference, but it has quite a significant impact on the accuracy of the modeling we can do. So just to give you an idea of that. So what we see here, this is exactly the same data. So this is the road network on the left, and then the dual graph representation on the right. So it's interesting to see that, this is fundamentally the same data, just different mathematical representation of that. And then to go from that to a generally applicable traffic model, what we need to do, we take Department for Transport traffic data, which has got categories such as cars, bikes, LGVs, so light goods vehicles, and that's directional at various different times in the day. And what they do, they survey major roads annually, minor roads slightly, less frequently really, but it's nevertheless a really rich source of data. I mean, you can enhance this using real-time data from services such as Waze or TomTom. Problem with that is it's paid for services, and so until we generate an income, we can't really include that, or we prefer not to. But what we get here is count data at specific locations within that network. And you've probably seen, if you're out driving in the UK occasionally, you see those folk with clipboards by the side of the road. They're not they're not car spotters, they're genuinely counting traffic. But that gives us an idea of just the traffic flow at specific points in the network. But then what we need is a generally applicable model so we can use that to predict the traffic at anywhere within the network. And that's where this sort of my particular troglodyte coder's ears pricked up, because machine learning loomed. I thought, oh, lovely. But unfortunately, we had to we follow the KISS principle, so keep it simple, in order to get the very first iteration of our model out and in front of users. So really linear regression beckoned. And it's a simple, really simple approach, and it's elegant, but as we'll see, surprisingly effective in this case. And as I've said here, the inspiration came from a really accessible paper written by Jaya Singh and a few others. And what we've done is we've tweaked their approach. Their approach was based in Asia, and we've tweaked it just to take account of probably some more accurate data we've got available in the UK, and also some of our sort of road network nuances. And I've got to say, we're not the only people or the first people to do this. There are other software solutions such as SDNA or CADNA, which can equally well model this. But we're excited to get into this sort of market. And what we think is we're providing an easily accessible, easily understandable solution where you don't need to be an expert in these particular fields in order to get an idea of how noisy your location might be. So how do we go about that? Well, in terms of sort of the parameters and coefficients we use to drive our model, in specific sort of traffic modeling, centrality measures have been the go-to metrics for quantifying this and looking at road networks and traffic flow. And so what we see here, we've got two of the centrality measures that we've used for Derby. The left in green, this is centrality, or betweenness centrality for Derby. And what betweenness is, it's a measure of how often a road segment, any particular road segment, lies on the shortest distance or the shortest path between any other two segments in the network or any nodes. And it's worth saying that shortest path doesn't have to be just the length of a path. It can also be measured in terms of time to traverse it or the angular change as you go through the network, or a combination thereof. And that becomes critical in the way we do it. We combine these few shortest distance measurements in order to get an accurate model. But effectively, the betweenness gives you it boils down to being a really good way of measuring pass-through traffic. And as you can see here, we get a higher value for the major roads, which gives us one sort of aspect to our model. But then on the other hand, we also need to sort of consider the more local origin destination journeys and how they're best represented. And that's actually done using what's called a closeness measure, which is the blue on the right. And that's a measurement of how close each network node is to all of the other network nodes. And so you can see really that there's quite a big difference between the two. But what it gives, these two figures give a very good visual indication, I would hope, that a general traffic model should include a bit of betweenness and a bit of closeness in order to be the most accurate that it can be. And what a result we get. I mean, Jaya Singh demonstrated really good correlation in their paper, and rather rewardingly, and I'll be quite frank with you, quite surprisingly, we achieved the same with a limited amount of input data, far below what you'd normally do for a sort of 4-stage traffic modeling data or some of the discrete element models that people use. And we get a slight increase on their published data. We're getting an R² there of about 0.9, which is pretty remarkable. And we don't use any factors in this. This is all just based on directly physical measured data. And so we get a really good correlation. And you can split the traffic data down into test and model development sort of sets of data, and we get a really good correlation between these. And it's worth noting actually that the parameters that you generate here can be generally, if you're particularly lazy or not lazy but short on time, you can apply that pretty generically to any city in the UK, and these simple parameters will give you a reasonably good traffic model in most cities in the UK. But notwithstanding that, we actually do local modeling because we have noted in places like Milton Keynes, which kind of fly in the face of the local vernacular or the normal vernacular, can make a big difference. Milton Keynes has got very limited wiggliness in terms of streets, but it's got a massive roundabout count relative to most other cities, which causes a bit of a headache to the analyst and the driver and the navigator, really. So, in terms of R², I think really we were very satisfied with these data. And you can see there's a strong correlation on that left-hand graph between this just on its own and traffic count. Well, and if you stir into the mix the closeness as well, you get very good data. So we were pretty gratified with that, especially given that we're a pair of engineers and not necessarily specialists in this area. But then we can extend these methods, and we can start thinking about, okay, well, if we're using it for traffic data, well, we could do the same for air traffic. And so that's what we can do. So we can suck in ADS-B data, which is readily available, and you can even get it with a dongle and a small aerial out the window. And so we use some slightly different software to provide a sort of noise contour map due to air traffic. And those two can be combined. We can build into the mix. We can do rail traffic. And what we're ending up with then is going back to those contour plots I first showed of just two properties with a nice, simple to understand contour map that people can then go away and think, okay, well, if I'm considering staying or renting in or buying a property, it's going to be noisier or quieter. But it does have some interesting, so there's some interesting sort of side data in this. So this is a graph that shows that same road network in Derby, but this is the quantified cumulative angle as you go along a particular segment. So effectively, it's the wiggly, how wiggly the road is. And as a youngster, my sister suffered tremendously with travel sickness, and I'm sure my parents would have been pretty happy. They'd have thanked me if I'd had this data to hand instead of the paper bag. But that's a slight aside. But nevertheless, it just shows that the data that we're using can be useful elsewhere. But it is a word of caution. That there's a real joy in using open source or other libraries. Someone else has done the heavy lifting, and all you have to do is call a function and pass in some parameters. But early on in this whole development process, we were warned away from doing comfort development. I mean, there's nothing I'd like more than to write the whole thing from scratch. But efficiency is the enemy of the enthusiast, really. But you do have to be very careful. As this example shows, what we're looking at here is 3 different routes between the same 2 endpoints on that road network, giving what are mathematically perfectly acceptable measures of the shortest distance. The red one, that's a route that's calculated using the relative angle of the endpoints of some adjacent segments, which is clearly, that is not the route that you or I would choose if we were going through between those endpoints. The yellow route, well, that's the one my sister would have liked, because it's got the minimal angular deflection at each of the junctions, so it would have been a fairly smooth ride for her. But the blue one, that by direct sort of inspection of the picture here, that's weighted using distance, angle change, and cumulative angle along the route. And pretty much, I think it's fairly obvious that that's the one we would choose. But that's not the default option in some of these libraries. So you've got to be quite careful how you utilize and use open source libraries. But all of this is written in Python, and by its very nature, Python's a sort of open language, and you can go in and inspect and marvel at the source code which other people have written, and you can validate and verify its intent. So really, what we've got and what we've developed is a fairly good solution, I think, in terms of providing people, the consumer in general, with an idea of how noisy or the environment around their properties might be, or properties of interest. But really, we are sort of standing on the shoulders of other people. We've stitched together the efforts of a lot of other people, okay, with some sweat and tears along the way, using open source libraries to do this modeling. And it has been a pretty gratifying process, really. I mean, I'm just acknowledging a few of the people there. The noise modeling software that we use is written by a French university, and we're one of the few commercial users. And then all of the OSM developers and contributors, really fantastic. And these data are readily available and downloadable in an easy form. So, and there are a few other people there, Jeff Boeing for his OSMNX library, which is fantastic, the MoMPy and Gabriel Filomena, and countless other open source. I mean, you can see from the screenshot behind there that really we use quite a lot of libraries in this process. And thanks obviously to Geomob for allowing us to present this. I think I've probably rattled through a little bit too quickly, but I hope I've given you an understanding of what we're trying to achieve, and the geographical data that we drag in order to provide a single, fairly understandable piece of data for the consumer. And then it just remains to put up our contact details and say, please get in touch if you've got any questions or comments, or if you're concerned about noise. And many thanks for listening, and I'll better pass you back to Ed now for Master of Ceremonies.